Hi, have you ever been swimming in the sea and noticed that the water at your feet is colder than the water at your chin? The tropical ocean surface warms and cools on a daily rhythm, forced by the sun and weather. But how does this diurnal cycle impact the atmosphere, particularly the clustering of clouds? To answer this question in large eddy simulations, we need to model the sea surface as an interactive boundary condition. My name is Reyk, and this work was done in the Atmospheric Complexity Group at the University of Copenhagen, together with my supervisors Romain Fiévet and Haerter. Give me 15 minutes and I'll try to convince you that we should revisit how we model sea surface temperature in idealized simulations of tropical convection. According to the new IPCC report, clouds are a major source of uncertainty for climate sensitivity, and their clustering is often connected with extreme events such as the devastating Hurricane Ida hitting New Orleans this year. In a changing climate, understanding the mechanisms behind the multi-scale organization of convection is crucial for society. Now, the temperature of the sea skin is a very important variable because it regulates the exchange of energy and moisture between the ocean and atmosphere. Many regions in the tropical ocean exhibit a pronounced diurnal cycle in sea surface temperature. However, it is not clear how this diurnal variability interacts with atmospheric dynamics. It has been proposed, for example, that diurnal warming could be important for the Madden-Julian oscillation by triggering the onset of the next active phase. And indeed, if we neglect diurnal warming, we can get monthly averaged heat fluxes wrong by up to 10 watts per square meter. So the diurnal cycle of SST can potentially impact even large-scale weather and climate. However, when we study convection in idealized simulations of the atmosphere, SST is often assumed constant in space and time, for example in studies under radiative convective equilibrium, or RCE. At coarse resolution, RCE simulations are known to produce convective self-aggregation. At 500-meter resolution, we get a different picture. On the left, we see an RCE simulation with constant SST. The moisture field stays homogeneous. Now, what happens if we let SST oscillate from day to night with a prescribed amplitude? This is shown on the right. And in this case, we clearly see how spatial clustering emerges. These results suggest that diurnal cycling makes a difference for convective organization. But neither a constant SST nor a fixed oscillation actually describe the real ocean. Aiming to get closer to reality, several studies have represented the upper ocean as a slab, with fixed depth implying a fixed heat capacity. The slab then warms and cools based on integrated surface heat fluxes and typically has an extra term to control SST drift due to excess heat. However, we argue that such slab models are insufficient to model diurnal sea surface temperature since they neglect the effect of wind-driven vertical mixing. At night, the temperature profile in the upper ocean typically looks like this, pretty flat. Then, on a calm and sunny day, it is common to have diurnal warming of up to 3 degrees Celsius or even more, where the profile looks like this, so most of the warming occurs in the upper meter of the ocean. This is because this profile creates stable density stratification, which inhibits mixing and accumulates even more heat up here. But then later in the afternoon, when the surface fluxes become negative and the ocean loses heat, this stable stratification becomes unstable, and we get mixing which transports heat downwards so that the profile looks more like this, and even later in the afternoon something maybe like this. If there's a bit of wind, then this wind also induces mixing, so the temperature profile will look more like this from the beginning. And if you have more than 6 meters per second, then there's so much mixing that the temperature profile is virtually flat. So the magnitude of diurnal warming is always a competition between thermal stratification and wind-induced mixing. Our goal is to build a simple model of diurnal sea surface warming forced by atmospheric conditions. To do this, we treat the problem as one-dimensional, and we assume that below 10 meters depth the temperature is constant in time, so all diurnal warming happens within this layer of 10 meters. At the surface, we now have the long-wave, latent, and sensible heat fluxes, and the solar short-wave radiation which penetrates the surface and gets absorbed below. Then we have heat transport due to wind-driven turbulence within the diurnal layer, and we imagine that there is also some internal time scale at which the diurnal layer mixes with the deeper waters below. Writing this in math, we propose one prognostic equation for temperature T as a function of depth and time. At any given time, the temperature change is given by the diffusion of heat within the diurnal layer, minus the mixing with deeper water, plus all the sources and sinks of heat from surface fluxes and solar radiation. The diffusivity kappa encodes the wind-driven mixing, and since wind stress is proportional to the square of the wind speed, we also let kappa scale with wind speed squared. Another modeling choice is that we make kappa a function of depth. At the surface, the diffusivity is now suppressed, as shown here by this vertical diffusivity profile. This is a crude way of accounting for stratification. The mixing with deeper water is simply modeled as a temperature relaxation to the foundation temperature Tf, with mu setting the relaxation speed. Note that deeper water gets mixed faster than water near the surface. And lastly, in the source term, we model the attenuation of solar radiation with an exponential decay law, where the coefficient alpha determines the depth scale at which radiation is absorbed. The surface fluxes are parametrized using standard bulk formulae. Our model is thus controlled by three main parameters: the eddy diffusivity kappa, the relaxation coefficient mu, and the light attenuation coefficient alpha. What are realistic values for these parameters? To find that out, let's look at some observational data. The dataset we use was kindly provided by Peter Minette, and it originates from a cruise in the Eastern Pacific and Gulf of California that took place in October 1999. The good thing is that this data includes radiometric measurements of SST directly at the sea skin, plus water temperature at 3-meter depth, and this at a temporal resolution of around 10 minutes. The plot here shows the time series of the temperature difference between the skin and 3 meters below. This difference, delta SST, is our measure of diurnal warming. So we see that the magnitude of diurnal warming varies greatly, being rather small in the first week and then reaching up to 5 Kelvin in the second week. The dataset also features atmospheric time series of wind speed, solar irradiance, and air temperature. So to estimate the model parameters, we now do the following. First, we code up the model using an explicit Euler scheme on a stretched vertical grid with a grid spacing of 10 centimeters at the surface. Then, we force this numerical model with some of the atmospheric data and compare the simulated diurnal warming with the observed one. This allows us to sample from the parameter space using Bayesian inference, and that gives posterior distributions for kappa, mu, and alpha, which tell us their most probable values. So, what does the diurnal warming look like when we run our model with these parameter estimates? Here's the result. Overall, not too bad. First of all, it's important that the model captures the wide range of amplitudes, from minor warming on day 2 to extreme warming on day 13. On some days, diurnal warming is overestimated or underestimated, which could be caused by some of the processes we neglect in our simplified model. The general features, however, are reproduced, including a slight nighttime cooling owing to the skin effect. Note that we can also find parameter values that perfectly model the 5 Kelvin peak, but then the overall performance is worse. Now, the shaded areas here indicate which time intervals of data were used for Bayesian inference. This means that everywhere outside these intervals, diurnal warming is predicted without any fitting. When we plot the modeled against the observed warming in a scatter plot, we see that indeed our model has predictive skill, with a correlation coefficient of 0.67 outside of the Bayesian training intervals. One nice aspect of this model is that it resolves the whole vertical temperature profile. On this heat map, where bright means warm, we can nicely see how the model naturally reproduces the deepening of the warm layer in the afternoons, which is something we also see in real life. Here's a quick video of how the shape of the temperature profile changes with time. On the left panels, we again see the time series from the cruise data. The right panel shows the modeled vertical temperature profile in red, and the wiggling blue cross at the top represents the observed surface warming for comparison. It is promising to see that the profile shows a similar qualitative behavior as observed profiles, even though the model is based on very crude approximations of turbulence and vertical stability. Earlier in this video, I argued that single-layer slab ocean models are insufficient to model diurnal warming realistically. But is that claim actually true? Let us find out. We can test this by coding up such a slab model and forcing it with the same atmospheric dataset as we did our model. As an example, this plot shows the results for a 1 meter thick slab in orange and a 2 meter slab in green. As expected, the 1 meter slab gives a larger amplitude of warming, but the amplitude seems relatively similar on each day, regardless of wind speed, and the warming peaks appear much broader than the observed ones. To visualize this more clearly, let us plot all diurnal warming data as a function of time of day, that's the top panel, and as a function of wind speed in the bottom panel. Note that the observational data clearly show a strong decay in amplitude with increasing wind speed. If we generate the same plots from our model output, we get this, revealing quite a similar wind dependence. But if we use the 1 meter slab model instead, the plots look qualitatively different. In particular, the magnitude of diurnal warming seems pretty much insensitive to wind speed. In conclusion, a slab ocean with fixed slab thickness does not capture the wind-dependent dynamics of real diurnal warming. To get diurnal warming right, we must include the effect of wind-induced vertical mixing, and our model offers a new approach to do this. Of course, the upper ocean has been studied for many years, and there are many existing models of diurnal warming, from full turbulence closure models to empirical formulas of the daily amplitude. Our goal wasn't to be more realistic or more sophisticated, but to contribute a model that is easy to use as a plug-in ocean for high-resolution atmospheric simulations. As simple as possible, yet as complex as necessary to also include the wind dependence of diurnal warming. To achieve this, our model consists of only one PDE for temperature, involving 3 simple and intuitive terms, controlled by 3 main tuning parameters. Numerically, we can solve this model with the Euler method, making it quite easy and affordable to implement in the code of a cloud-resolving model, and this is what we are planning to do next. While we only use one dataset to estimate our model parameters, this dataset includes observations from different locations, both in the open Pacific and in the Gulf of California, where the optical and dynamical properties of the ocean are quite likely to be different. This could suggest that the model is suitable as a generic plug-and-play boundary condition, mimicking tropical ocean conditions. Thank you very much for your interest. If you would like to learn more about this research, please check out the GitHub page by scanning this QR code here or send me an email. I hope that our model can be useful, but either way, it can at least be used to create pretty pictures like this one. Thank you. In addition to my supervisors Romain and Jan, I'd also like to thank Peter Minette for the dataset, Peter Ditlevsen for co-supervising this project, and Gorm Jensen for helpful discussions.